So first thing I want to do here, if somebody has a calculator, let's just verify that this formula is kind of right. So what would e to the first power be according to this formula? Well, e to the first power, isn't e like 2.718? Okay, well, let's try and convince ourselves. I'd like for you to plug 1 in, right? We're replacing the x with 1. This should be 1 plus 1 plus 1 over 2, 1/2, plus this one is 1 cubed is 1 over 3 times 2 is 6, plus the next one is 1 over, that's 24, and then plus the next one, 1 to the 5th is 1, and then that's 120, and I think I'll stop there. So on your calculator, I'm going to do it on mine as well. Do 1 plus 1 plus 1/2 plus a 6 plus a 24th plus 1 over 120. I get a decimal answer. If I stop right there, okay, if I stop with just these, I get 2.71667. That's what I'm getting for those first few added together. Now that's not 2.718, right? But guess what? The further I go, the closer it gets to E. In fact, if you could go forever, it would converge to E. So E is one of those numbers we talked about. Remember the irrational, the non-terminating, non-repeating decimals? You can actually use this formula to get more decimals. All right? So in Cal 2, we proved that this is true. Let's now accept that that's true. And now I'm going to ask you to take its derivative. This is the cool part. I think it's cool. So the derivative of this function is, well, if that's what the function is, let's take the derivative of that. You have a bunch of pluses, don't you? So you can just take derivative of each one. What's the derivative of 1? 0. Okay, 0. Plus, what's the derivative of x? 1. Okay, here, be careful on that one. That x squared over 2, that's really 1/2 x squared, right? That's really what that is? So if I ask you to take derivative here, the 2 would come out, right? 2 would come out and cancel. You just get what? X, right? So that's x. Plus, look at this one. What would happen to take derivative here? The 3 would come out and cancel with the 3. I would have x to what power on top? Squared. And what's still left on the bottom? 3 canceled. Over 2, right? Let's do the next one. Here, the 4 would come out, cancel with the 4. I'd have x to what power on top? What do I still have on the bottom? 3 times 2, which is 6. Keep going. This one, 5 comes out, cancels with the 5. I get x to the 4th over 4 times 3 times 2. Do you see anything? What's the next one? 6 comes out, cancels, x to the 5th over, what's still there? 5 times 4 times 3 times 2. Do you see it? That's exactly the same thing as it was. This is exactly this, isn't it? Look, take away the 0. The 0 has no impact on this. 1 plus x squared over 2 plus x to the 3rd over 3 times 2 plus x to the 4th over 4 times 3 times 2. It's the same thing. And because it's infinite, right, they'll match the whole way out. There's no other function that does that or behaves that way. Did someone have a question? Thought I heard someone say something. Yes?
So this is off topic. How did someone discover this?
Well, that's what we talk about in Cal. What we asked as mathematicians is if you take a function, is there any way that we can approximate that function with a polynomial? And then what we discovered is that we can actually come up with like a generic formula for getting an approximation, and it's just what we do is we try and make this approximation match this function at one point. And then we say not only do we want this approximation to match this at one point, we want the slope of the tangent line to be the same at that point. And then we want the first derivative to be the same. And then we say we'd like for the second derivative to be the same as well. And then we'd like the third derivative to be the same, and the fourth, and the fifth, and the sixth. and forever. And by using that procedure, we can actually generate this what's called the series. It's called the power series. So again, the carriage is in front of the horse. There is a very easy way to do this using what are called Maclaurin series. I don't know if that answers your question. So it's in Cal 2, it's called Taylor-Maclaurin series. But somebody definitely struggled with it for a long time, right? I told you there were two fathers of calculus, right? Remember me telling Leibniz and Newton, right? But I said Leibniz, he had some limitations on his calculus. Leibniz never figured out this series. Leibniz never got to that. And so Newton had problems that he could easily convert to their power series, and then he could do whatever he needed to do with them. Believe it or not, this is actually very, very valuable, because this goes back to a computer again. Yeah. This goes back to a computer. When you go to your calculator right now and you type in, if let's say you're in radian mode and you type in sine of 2 on your calculator, right? What did your calculator do? Do you think your calculator just has stored in its memory what sine of 2 is? Or do you think it did some operation to get an answer? It did some operation, right? Now, does it have any idea, like unit circles? Is that the way a computer works? What can a computer do? What kind of math? What can it do very quickly? Arithmetic, right? It can add and subtract super fast. It can multiply and divide, right? These are basic 4 arithmetic operations. That's all a computer can do. So what did it do to get that answer for you? I'll tell you what it did. It used the fact that sine of x has a power series. You've never seen it before, I'm sure. Maybe you have. It's this power series. Y'all see that? Okay, so if you plug in 2, what your calculator did is it plugged into here, to here, to here, to here, to here, to here. And whoever programmed the calculator has it terminate at a certain part of the series and it gives you an answer. And if you want more decimals, you can go into the computer and you can say, I want more decimals, and it'll go further out into this series. All this is just multiplication, addition, subtraction, right? That's all this is. So if I plug into, I'm not going to do it on my calculator, but you would get the answer for that, and it would match what your calculator gave you. No, we're not taking derivative. No, just plug. If I said plug 2 into that, you'd replace these with 2's. Does anybody have a guess as to what, this is called the power series. Any guesses as to what the power series is for cosine? What do you mean? So this is actually the beauty of power series. Do we know what the derivative of sine is? Cosine. So the derivative of that should be the cosine series. Differentiate this. What's the derivative of that? 1. Okay. Minus. Okay, here, can y'all see the 3, 2, 1 down here? Or 3, 2? When the 3 comes out and cancels out, what am I still left with? X squared over 2. It'll be 2 factorial. And then I'll have plus, and now the 5 comes out, cancels. I'll get x to the 4th over 4 factorial, and then this one will be x to the 6th over 6 factorial plus x to the 8th over 8 factorial. They're all even. These are all odd. Don't you learn in pre-cal that sine is an odd function and cosine is even? Right? Why do they call it odd and even back in the day? Well, you didn't realize it then. It's because any odd function has an odd power series, and any even function has an even power series. And other functions like tangent, or e, look at e. E has a mixture of odds and evens. It's neither. It's neither odd nor even. So, okay, yeah, we're going down another rabbit hole, but I'm trying to get you to, I guess, appreciate the fact that the derivative of e to the x itself is the profound part of what makes e to the x so special, is that it is its own derivative, and it's the only function that behaves that way. All right. Let's do a couple of practice problems. I'm going to let you do these. So, you know how I was showing you that problem with the piston? That actually came off a review. That was a test 2 review. So I'm going to kind of zoom this out a little bit. Can you all see that enough? Yeah. No? Just try and do like, you know, one from here, one from here, one from there. Enjoy. All right. And if you do a couple, try to do as many as you can. Let's say we'll go with this for like, I don't know, 10 minutes or so. Okay, you can work together, talk to each other. There's not a quiz grade or anything. I just want to see how comfortable you are with this idea. All right, first one. I'm just going to put the answer. So it's itself, okay, times, and now I have two terms, so I need this in parentheses, 3x squared plus 1. The next one is almost the same. It's itself, but then I have to throw a natural log 4 there, and then I can do 3x squared plus 1.
Does it matter which one you have in parentheses?
Does it matter?
Like if I would decide to put parentheses over ln4 and just leave 3x squared plus 1 alone?
That would still not work. Yeah, if you do parentheses on this and then leave that not parenthesis, then it's going to look like all you're doing is multiplying the first two.
Why did you put an ln in the first one?
Why? Well, because it's e. If I did ln of e here, ln of e is 1. Now you can do it, but just remember it turns into a 1. All right, this one should be, well, derivative natural log of something is 1 over whatever was there times the derivative of what was there. And then you could slide that in parentheses on top. This one is almost the same thing, except when I put x cubed plus x down here, I need it in parentheses because I'm going to multiply that times natural log of what? 10. Because this is really log base 10. And then when I'm not done, times now the 3x squared plus 1. And then this one is almost the same as the one above it, but there's a natural log of 4, and then times 3x squared plus 1. So these problems were just to kind of like make sure you understand the differences, right? Do you get hiccups a lot?
Yeah.
Oh, you do? Okay. So it's not just something like in this room, or it's not us. We're not doing it to you. Okay. All right, how about that one? What am I going to do to take derivative there? Product rule. There's your product. So derivative of the first one times the second one plus, now what's derivative of e to the x? Itself times root x. The difference between that one and the next one is we still have product rule, right? But the derivative of the first one this time is 1 times e to the root x plus, now here's the part that's a little tricky. You're doing the derivative of e to something, right? E to a box. So derivative of e to the box is itself times the derivative of the box. So the derivative of that should be itself, e to the root x, times the derivative of the root x, 1 over 2 root x. But then I still have to multiply that by what? X. See the difference between those? This right here is my chain rule on e to the root x. What's that? Okay, so I had y'all write this down, right? Derivative of e to a box is itself times the derivative of the box, right? Okay, so when I take the derivative of this right here, I'm in the middle of a product rule. Derivative of this one times that one, plus, when I do this one, that's a box. E to a box. So what's the derivative of e to the box? Itself times the derivative of the box. And then finish up the product rule. Any other questions on that one? Sure? Last one. For the last one, we have a square root on top of everything, right? So I've got to do chain rule first. I have the derivative of the square root of my hand, which should be 1 over 2 roots of my hand, times, now inside product rule. So I need that in parentheses so I can do my product rule. Derivative of the first one is 1 times the second one, e to the x, plus derivative of the x is itself times x. Okay, I hope that was helpful. I mean, I'll send you all this review pretty soon. There's more here. Look, there's more, lots more. I tried on this review to give a bunch of problems for practice here. Pardon? The next test is a long way away. In fact, we need to talk about this. We might want to change this because our next test, right? Oh, wait, are we off on Tuesday?
Yes.
Oh, shit. So we're not going to meet again until next Thursday. Forgot about that. Sorry, that's so sad. Okay. I recommend you do the homework. Okay? Do the homework for 3.3. We have not done 3.5. 3.5 is going to be pretty quick. We're going to knock that out fast when we come back. But look at, we don't have an exam until almost the end of the summer. Right? It's like 2 days before. So we might consider moving it, but I'm not sure where we would want it.
Do it after it.
A week before, maybe? I don't know. Or we just leave it there.
Or do it Tuesday instead of Thursday.
Or we just get rid of this and just get rid of that and just make a final exam and make it worth like a huge part of your grade. No? No? Oh. Okay. All right, we'll talk about it. So please, please at least try and do the homework through 3.3. If you want, I'll finish up that thing if y'all want to see it. The one with the question about the log property? Okay. It was this property, and if not, have a good weekend, have a good break, have a good holiday, and I will see you on Thursday of next week. This one? Yeah, it's too easy to find the answer. I'm sure if you looked it up, you'd be able to find it too easily. What?
Oh, you can find it.
Yeah, you'd be able to find it too.
I was like,
No, not doing it. I think finding it would be too easy. So what did I do? I want to follow what I had done. I had said, let's start with this fact that, I don't remember if I did a, I think I did a to the x plus y equals a to the x, a to the y. Is that what I wrote? Or did I do it the other way around? I did that?
Yeah.
I did that way? Okay, and then I did the log on both sides, right? And that became this. Right? That's where we were. And then on the left-hand side, the log base a and a kill each other off. And we were left with x plus y equals log base a of a to the x times a to the y. And this is where we're kind of stuck, right? All right, the next step on this is not a natural step. That's why I just didn't want to just show it to you. But let me try and explain what I'm going to do. I'm going to try and make this become something nicer and this become something nicer. And the way I'm going to do it is I'm going to replace x with something so that it kills off with the a. In other words, I'm going to replace x with a logarithm so that when they go together, the a and the log kill each other off. So I'm going to make a substitution. This is the not natural step. I'm going to let x be equal to log base a, and I'm just going to make up a letter here of m. And I'm also going to let y be log base a, and let's just say another letter, n. So anywhere I see x, I'm going to replace it with this. Anywhere I see y, replace it with this. So on the left-hand side, what do we get? X is log base a of m plus y, which is log base a of n. That must equal log base a, and now here's the really interesting part. This is a raised to the x, but what's x? Log base a of m, and then I have a raised to the y, which is log base a of n, right? What happens when I do a to the log base a of m? They cancel and I just get what? M. And here they cancel and I just get n. So this is log base a of m times n equals what?
Log 8m, oh my god.
The product of these two things inside of a log equals the sum of the two logs individually. Yeah. Change of base. I didn't use change of base.
No, because you let x equal.
I used this. The big property I used here is that if you have a raised to the log base a of anything, I'll call it x, that's just x. I use that here and here, but that gave me the m and that gave me the n. But what motivated me to do that, right? Like what made me want to do this substitution? That's the non-natural part. I think it would just be you looking at this enough and trying to think about what you would like this to be. Like you see that you have a product here, right? And you see that that's a sum. So you're almost to this, right? You have a product in here and you have a sum here. So is there any way that I can somehow turn this into logs and that into just nice things? Well, I can turn that into something nice if I make that a log base a of m. And I can make that nice if I make that log base a of n. Then they become m and n, and then the other sides become the logs. So it's not natural. I'm not sure. If you look this up online, I'm not sure what you would get. I'm willing to bet a lot that that's not the way other people would prove it, but it's proved. I mean, it worked, right? Okay. Have a good weekend. Have a good 4th of July. What's up?
Can I erase that?
Do what? I'll get it. I'll get it. No problems.